Year 12. This is the last video. Well, I'll probably do this in two parts, to be honest, but it's the last video on momentum or to do explosions. All very exciting stuff. So, to get you going, what I think is very important with these is now we've got a video of this. And the reason why not, you can't just pause the video, look at this, and work it out yourself. I'm going to give you the answers at the end of this little video somewhere. Anyway, you've got a spacecraft use rockets to accelerate away from the ground during liftoff, and the rockets eject large quantities of gas at high speed towards the ground. And here are some statements about the spacecraft during liftoff from the moon. And what I want you to do is choose the correct answers. So I advise you, pause the video and work out what the correct answers are. And then at the end of the video, I'm going to explain them. So, to go with this is a really cool device. I've got one. I used to call it a Gaussian gun, but this video calls it a Gauss gun. Fine. It's a really cool device. I've got one in my lab, and I look forward to showing it to you when we get back into lab again. Anyway, it's a really nice bit of interesting physics, and can you work out how it works? So to show you this I've got a cool little video here. Watch this. I'll get rid of that first of all. We don't want that there. This is a cool device.
Hello and welcome to the First for Magnets YouTube channel, and thanks for watching our most recent video. Here in front of me I've got what we call a Gauss gun experiment. It uses mild steel ball bearings and super strong magnets to fire one ball bearing off the end of the track. Here I've got a trigger ball bearing which I'm going to roll towards the first magnet. As it gets closer it will accelerate, and the energy will transfer from this ball bearing through the magnet to the ball bearings on the other side. This will repeat all the way along the track until the ball bearing at the very end is fired off. Okay, let's see how it works. Okay, so you can see we've got lots of cameras set up here, so we're going to show you this experiment in super slow motion. The trigger ball bearing accelerates as it gets closer to the first magnet until it collides, at which point the energy is transferred through the magnet to the two ball bearings on the other side. As the magnetic attraction with the ball in direct contact is greater than the energy transferred by the collision, the first ball bearing stays in place and the momentum transfers through to the second. The second steel ball is then propelled at the same velocity, minus minimal losses occur during impact. It then picks up speed as it approaches a second magnet. Each collision repeats with each ball travelling slightly quicker, minus rolling friction, air resistance and the magnetic force holding the ball in place. For more information on how...
Now, my son, Torrin, has got one of these, and I've got one in my lab. When he watched this video, he wondered where it was, and I said, it's in school, I'll get it for you sometime. Anyway, it's really cool this, and really shows you conservation of momentum. So what you've got is a ball bearing going here, and these obviously magnets attract it, and it will pick up speed because there's a force in it due to magnetic fields. And in fact, it gains kinetic energy, but when it whacks here, you do have conservation momentum where this hits it, wallop, and you've got mass times that velocity. Therefore, at the end, when this moves away, it must move away with the same velocity because it has the same mass and the one ball bearing is leaving. Main reason that one sticks down, that one leaves, well, think about it, near the magnet, you've got a stronger magnetic field. That's got a weaker magnetic field as it moves away to the magnet. Hence, that's the one that can leave. Each time, obviously, you've got more magnets going down, it's going to get attracted to the next magnet and it keeps getting a higher kinetic energy. Therefore, that's why the speed increases going down in loops, well, in segments going through. But this really nice way of showing you conservation momentum in action, and that's the Gaussian or the Gauss gun. But what I want to do now, go through in detail, is applying conservation momentum to explosions, and also how you calculate the unknown velocity of an object after an explosion. So to show you this I've got little videos going here. Now, well, this is a simulation rather. Now, this is going to be a straightforward explosion. Now, clicking on here, what you've got is two trolleys, A and B. I do this in a lab where I have basically got the two trolleys, and they've got these little bolts here that are held together. Well, they're pushed in by a spring, and when you let go, one pushes the one pushes the other one, and they push apart. But I'm going to show you throw it through a simulation here. So mass A and mass B each have got mass 1. Now at the beginning, obviously you've got UA and UB, they both got the set velocity of 0, and afterwards A is going to have velocity VA and B is going to have velocity VB. This shows you momentum before, and afterwards the momentum of this one is going to be 0, the momentum of this one is going to be 0. And you can see the momentum at the end afterwards as well. Now here, what I'm saying is I'm giving an energy of 2. In other words, here, this is going to be explosion. The initial energy chemical store is going to be 2 joules. But beforehand, the kinetic energy of A and B, both are going to be 0 because they're stationary. Now, how exciting this. And there you go, got an explosion. Now, when you got the explosion, you can see the 2 moving away. And VA is going to have a velocity of minus 1.4 and VB is going to have a velocity of 1.4. They're going to be negative and opposite because I'm saying going that way is going to be negative and going to the right is going to be positive. So the left is negative to the right. So the right is positive, to the left is negative. Now if you look very carefully, then I can work out the momentum of A is going to be the mass multiplied by the velocity, which is then going to be mass of 1, therefore it's going to be minus 1.4 because the momentum is a vector quantity, and B is going to be 1.4 going to the right. Has the momentum been conserved? Well, it has, because the initial momentum is going to be 0, and the final momentum is going to be 0, minus 1.4, and then you've got plus 1.4. When I look at the kinetic energy, well, beforehand it's 0. Can you see now, by using a half mv squared, I can have the kinetic energy of A is going to be 1, by using a half multiplied by the mass multiplied by v squared, and again the other one is going to be half mv squared. Half mv vb squared is 1. 1 plus 1 has to equal that 2 which I started with. Therefore, kinetic energy is conserved. Now, thinking about it now, if I make the trolley B now 3 kilograms is 1 kilogram. Can you predict what's going to happen to the speed now? Now, start with exactly the same energy. Explosion is going to happen. Exciting. Okay, can you visibly see now B is a heck of a lot slower? Well, does that make sense? Well, it does make sense because now, again, the initial velocity is 0, the initial momentum is going to be 0, and the initial kinetic energy is going to be 0 because it's not moving anywhere. Now VA is minus 1.7 and VB is 0.6. Now, working out the momentum, because now you've got the mass is going to be 1 and 3, is when you work it out, that's going to be minus 1.7, that's going to be plus 1.7. Well, again, won't I have conservation momentum? Correct, that's being met. Look at the kinetic energy before, it's going to be 0. After the explosion, 1.5 and 0.5 has to still be equal to 2. But when you look at the speeds, they are, aren't they, apart from got a bit of rounding up here, the ratio of 1 to 3. Okay, it should be 1.8, it's not quite there, but it's a rounding up issue with it. But this one should be 3 times slower than that one because it has to make the momentum going to be equal before and afterwards. And this is the key behind explosions and momentum. So getting back to here,